Good morning, everybody. Well, usually speakers, when the feedback from the audience is so weak, always say, well, we can do better in good morning, but anyway. I'll talk about the topic of Industry 4.0 and the fourth industrial revolution, which is also relevant for the whole topic of IoT. And the talk is structured in two sections. First, I will give an introduction what Industry 4.0 is all about. And then I will talk about more a little bit what Siemens is doing in this direction. And when talking about Industry 4.0, let me first explain to you the meaning of the term per se. It's a term which has been much talked about, which was also a lot of in the news here in India, especially as India was the partner country this year in Germany at the Hannover Messe, and Prime Minister Modi went there. And one of the main topics of the Hannover Messe this year was this Industry 4.0. So first of all, industry, the first part, that is the German word for the term English word industry. And the 4.0 refers to the fourth industrial revolution. We'll also explain what are the four industrial revolutions. But what is important to note is it's an initiative from the German industry, the German manufacturing industry, supported by the German government, to ensure the competitiveness of the German manufacturing industry in the age of the internet coming into manufacturing. And that brings me to the four different revolutions we have seen so far in manufacturing or in industry. The first one was when steam engine came into production, into manufacturing. And that was in the 18th century, and the first example were looms that were powered by steam engine. Then later on, in 1870, we had electricity coming into factories. And example, the first one that was in Cincinnati, a slaughterhouse, where there were conveyor belts which were automated with electricity. Then the third revolution came in 1969, when PLCs, programmable logical controllers, came into factories and when computing power was made available for production. And the latest revolution that we are seeing, the fourth revolution, started about in 2011. And this is in principle when the Internet of Things and cyber-physical systems became a part of manufacturing. What is also interesting to note when we talk about IoT, sometimes people feel it's something which is a new trend. I don't know if you ever thought about or if anybody knows when the term Internet of Things has been mentioned for the first time. Any idea? Any guess? 5 years ago? 10 years ago? Who is of the opinion that it was more than 10 years ago? Can you raise the arm? Okay. Less than 10 years? It was in 1999, 16 years ago. There was a person, Kevin Ashton. He was the director of the Auto ID Lab, and he mentioned this term in a presentation he made for Procter & Gamble, where he connected RFID with the internet. So in principle, IoT is a relatively old term, but still there are doubts whether the Internet of Things is a vision or something that is already existing. What you see here, this is from the Boston Globe magazine December issue 99, so this is more or less exactly 16 years ago. There was an article on smart buildings, and there was an article also, it's a nice story about the milk and the fridge. And that was also, let's say, an idea which has been communicated by the MIT Media Lab from Nicolas Negroponte. And it talks about that you have intelligent, in your household, in a smart house, you have intelligent objects or things which can talk to each other. And the story about the milk in the fridge is, number one, the milk bottle has a certain intelligence and, well, she knows the daily consumption. She also knows the current, the milk bottle at least, how much milk is still in the bottle. And as long as the milk bottle is close to being empty, it will send a signal to the fridge. Hey, dear refrigerator, I'm going to be empty today with the daily consumption. Could you please inform, let's say, the head of the household that we need to buy some milk? The refrigerator will send, let's say, a signal maybe to the head of the household when he's leaving the house. He has some kind of a storage or chip in his shoe, will send a signal. We need to buy milk, maybe some other things. On the way to the office, this information will be passed to the car. The car will check the supermarkets where we have the best offerings, and on the way back, we have the information that we could go shopping at the supermarket A, where we have one offering, or supermarket B, where we get a better offering. And that is the story of the milk in the fridge that has been published in 1999. Now, if you read the article from this lady from the Mayo Institute, which was published 2014, she says the milk in the fridge, they don't talk to each other. Not yet. And she's of the opinion that Internet of Things is still a vision. She also asked the question if it's desirable that this mission comes, or this vision comes true at all, because there's always still a weak link in the whole system, and those are the people. As long as the milk and the fridge talk to each other, I mean, things probably will work out. The minute people come into the picture, it becomes more complex. And the fourth recommendation she's making is, on the way home, don't forget to buy milk from the supermarket. So, IoT, is it still a vision, or is it about to come true? There are other opinions, and this is probably all why we're here, who say it's not a vision of the future, it's becoming reality. And if you read this article from Michael Porter in the Harvard Business Journal, he says in principle that the Internet of Things is reality, and he also gives a number of examples where in closed systems it is reality. Mr. Kirloska, you may excuse that I'm using an example from Tesla. I don't know if Toyota can offer something similar, but Tesla, today, it's the way if the car figures out that there is a need for repair, it will automatically communicate, download the required software, or if the car has to go to a garage to do some physical repair, it will coordinate automatically a date. It will even organize the pickup of the car, and maybe that you have, for the day the car goes to the garage, a cab. So it's really, let's say, an Internet of Things, a closed system for this vehicle and the repair. Another example is in wind power. If you have a wind park, and the wind is blowing, and the different windmills, I mean, they all stand in a certain order, and there may be an impact on the efficiency of the wind blades, depending on the strength of the wind, the direction, and if the windmills are connected to each other, they can communicate with each other, and the blades can be changed, the direction of the blades, in a way that the efficiency of the blades is maximized. So this is in principle what the Internet of Things, it's real, it's becoming real, and we even have systems today that are in place in closed environments. So this is one part of the fourth industrial revolution. The second part are cyber-physical systems. And cyber-physical systems talk about the real world on one hand, where you have, let's say, your physical systems, and on the other hand, you have a copy of the real world in software. That is what is called typically a digital twin. And this digital twin will evolve over time in development. That's also indicated in the lower part of the picture where this twin is growing and growing. The more information is added, and you can, for example, have information where you can simulate certain behaviors. In automotive industry, for example, how it will look like if you have a crash of a car. So this is what is called cyber-physical systems, and those together, Internet of Things with cyber-physical systems, are getting into manufacturing. That also means, if you look at the future of manufacturing, there are certain key elements that are important. This is the cyber-physical systems, what I've mentioned before, but also the production networks, as well as the integration of the virtual world and the real world. And based upon that, the German automotive or manufacturing industry, they came up with certain recommendations. This book, the title page of this book is publicly available, so you can download it on the internet. It's the recommendation for the manufacturing industry, how to implement the Industry 4.0. What is required for Germany to ensure that the manufacturing industry remains competitive in the future. And one thing, of course, is the use of cyber-physical systems. And so that Germany concentrates on the technology of cyber-physical systems. And the second topic is the integration of information and integration technology in different aspects. And those aspects are, in principle, three: integration of the value chain, which is key for making Industry 4.0 come real. Number one is the horizontal integration through value networks, where you have an integration with your suppliers that you also can jointly deliver and produce something. The second topic is the end-to-end digital integration in the production lifecycle management. And the third one is the vertical integration in a network manufacturing environment and the systems. So those are the three main recommendations from this Industry 4.0, where companies should work on, and based upon that, also a number of different research topics have been identified and nominated. In addition, the German industry generated an ecosystem where they collaborate with different bodies. That is what is called the Platform Industry 4.0 and its environment. A number of those bodies are shown on this slide. So it's a whole initiative movement in Germany to make sure that the IoT and cyber-physical systems are implemented in manufacturing in the environment in Germany. Now, if we look at what we at Siemens do in this direction for Industry 4.0 in special and digitalization in general, and well, with Industry 4.0, what we do, let me start with a short video which also explains a little bit in detail or gives an idea about the initiatives at Siemens.
A vision of tomorrow's manufacturing. Products finding their way independently through the production process. In intelligent factories, machines and products communicate with each other, cooperatively driving production. Raw materials and machines are interconnected within an Internet of Things. The objective: highly flexible, individualized and resource-friendly mass production. That is the vision for the fourth industrial revolution. A look back at history. At the end of the 18th century, the first steam engines and the intelligent use of hydropower revolutionized production. The late 19th century saw the rise of electrical engineering and mass production. The first moving belt conveyor was used as long ago as 1870 in the slaughterhouses of Cincinnati, Ohio. In the mid-1970s, electronics and IT began to expand rapidly into industry. Siemens developed the first SIMATIC. Production became increasingly based on computer-assisted controls. The fourth industrial revolution is still a vision. Experts believe that it will only become a reality within the next 20 years. In intelligent factories, everything is interconnected wirelessly. At the German Research Center for Artificial Intelligence in Kaiserslautern, this future can already be experienced right now. Research is underway here into exactly what the industrial production of tomorrow will be like.
Fabriken werden zukünftig aus Bausteinen bestehen, aus smarten oder intelligenten Bausteinen, wie man es nennen mag. Vergleichen wir das vielleicht mal so ein bisschen mit einer Lego-Steinwelt. Das heißt, wir haben standardisierte Bausteine, die wir hoffentlich relativ einfach zusammenstecken und zusammensetzen können. Jeder dieser Bausteine hat bestimmte Funktionalitäten und wir können sie zukünftig in einem solchen fabrikinternen Internet dann kombinieren.
A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed. Which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, a computer checks whether the bottle has actually been produced as desired. Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines, and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as cyber-physical systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyber-Physical Systems. Das heißt, Sie haben autokrate, selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen. Und dadurch letzten Endes Produktion optimieren. Ja,
die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes. Because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation entsprechend ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At Corporate Technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the Internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
We've prototyped capabilities in a PLC to access big data in cyberspace in real time. And we've also enabled a network of PLCs to connect to a dynamic simulation of the entire physical process.
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
Well, that was a little bit an insight what we at Siemens do. And in the beginning of the presentation, I mean, you heard the comment that it's still a vision, but this clip was 2 years old, and Since then, we didn't rest. We invested a lot, and I would say in the meantime, it has become reality. What you've seen here, the scenario in the lab with this production, that the bottle knows exactly what kind of ingredients are required, is what we presented at the Hannover Messe this year. We had a production facility where you really could see cyber-physical systems, mass production, individualized, and I also saw a clip where both the German Chancellor together with Prime Minister Modi visited the booth and had a look at it. So number one, it's real, and number two, the way we look at it, we are, let's say, enabler in terms of in automation industry for making Industry 4.0 come real with the integration of product lifecycle management, totally integrated automation, and manufacturing execution systems. This is in principle a tool chain which enables you to go from product design to planning, engineering, production execution, so covering the complete process. And that is what is called the Digital Enterprise Software Suite. So our answer to the requirements of Industry 4.0 with from left to right, from the product lifecycle management tools like Teamcenter, NX. In manufacturing execution systems, we have Simatic IT, where we offer systems like plant information management, maintenance management, monitoring, and components like that. And on the right-hand side, then the totally integrated automation, where we offer a seamless engineering across the shop floor for the controller systems, for the hardware, the sensors, actors, and everything. In addition, beside those software suites, we are also looking into digitalization per se. So the way Siemens is structured today, in principle, we have three main topics. One, where we are focusing on the pillars of our business, electrification. The second one, automation. And the third one is digitalization. And what we do is we take our domain know-how and product know-how from electrification, automation, and add it to offer, on the one hand, digital services, vertical software, as well as enhanced digital products in electrification and automation. And if you look at this in more detail, that also what was yesterday announced in Munich, there was a big event with our CEO, Joe Kaeser, and our CTO, Siegfried Russwurm. And what they talked about is the next step of digitalization going beyond IoT, and that is what we call Web of Systems. Web of Systems refers to devices that are able to communicate, but not only via the internet, but also directly. That means communication can happen via internet, that is what is Internet of Things, but also in a closed environment where it's not necessarily desirable that the communication goes into a cloud where you not necessarily will have all the control, so that you also have intelligent devices that can also do some kind of the processing power in itself and communicate directly to each other. This is the concept of Web of Systems, which has been announced yesterday in a big event in Munich. And the second topic is we also offer a platform for the whole topic that is called Synalytics, which is our industrial data analytics platform, where we offer services for data analytics, but also for remote communication and secure access to systems. At the moment within Siemens, we have about 300,000, more than 300,000 devices connected to this platform, but we are also offering it as a product. And if you are more interested in this specific topic, Web of Systems, Synalytics, at 11:35, there's also a presentation from a colleague of mine, Bernhard Lang, who will specifically talk about that topic. To summarize, Industry 4.0, what I've mentioned in the beginning, refers to the fourth industrial revolution. That means Internet of Things plus cyber-physical systems getting into manufacturing. From my point of view, it's not a vision, it is reality. Today, there are factories worldwide where it's already implemented. There are tools existing which can help you to create, to make the fourth industrial revolution come true. The next step, what we are working at Siemens, what we announced yesterday, is the web of system, and the tool for that is the platform Synalytics. Thanks a lot, and like I said, if you would like to know more, at 11:35, colleague Bernhard Lang is talking about the topic. Of course, yes, okay, yeah. Just been informed that we have a few more minutes and that we have time for questions if somebody would like to ask something. First question is always the difficult one, most difficult one. That's why I always say let's start with the second question first. Yeah. Do we have a mic for?
My name is Satyan Narayan. I worked on this IoT way back in late 90s and with a French company. And I have a question on risk.
On risk?
Yes.
Okay.
Because the problem is I used to work in an unmanned unit. It was an unmanned plant. There was nobody. I used to remotely monitor it. And I also used the Microsoft technology to take the data and analyze it. But the question is on risk because nobody was understanding then what was the problem. And the question here is the risk in terms of safety, in terms of because the infrastructure wasn't there to do this. And so my question is, how do you assess risk in such, because you're dealing with a physical system?
Well, in the end, it also depends on the kind of system you are using. I mean, this is why, for example, we worked on the Synalytics platforms, where we especially try to have a secure system also in terms of access. So you need to have the right systems in place which secure your environment, otherwise you won't be able to overcome this risk.
No, because, my question is, if there's an unmanned unit and something's going on, but if there is, there could be issues of safety, because some people goes and interface, it will disturb.
Yeah, but see, if you look at a safety issues, for example, even if you have a plant which to a large extent is without human being, everything is automated. Usually, at least the way I know it, you have robots which are also, let's say, will recognize if there are, let's say, human beings in the way that they stop in their movement. I know it, for example, I can't quote an example from healthcare, but from automotive or manufacturing, but in healthcare, we also have robots, for example, in angiography, where the robot rotates around a patient with X-ray. And there, if there is a movement, for example, the arm will automatically identify that there are people and will stop the movement. And there are safety mechanisms in place. Of course, you have to implement them. So from my point of view, there's nothing which prevents you to use this kind of technology. And Mr. Kieloska probably can answer this question in an even better way.
See, we use a lot of this kind of stuff you're talking about in car manufacturing. But the real key to get the output, safety, quality, with a lot of automation is actual human skill. If you cannot, the more sophisticated your manufacturing setup is, the more sophisticated your equipment and more software and automated systems you're using, the more the training you have to give to the people who are involved in working in it. The skill level has to be at the same level as the automation level, the human skill level. Yeah. We have in our supplier base maybe about 200, 250 suppliers. And our average PPM is about 4, which is pretty much world class. We worked hard with suppliers to get to that level. 80–90% of our suppliers are 0 ppm suppliers. So if you're looking at automation, first is you need a 0 ppm supplier. You need 0 ppm in your process control, in your quality control. A lot of it happens with machinery and automation and this Internet of Things and communication, but a lot more happens with just human skill. It needs very, very high level of human skill, so high level of training. Yeah. That's the only way you can take care of risk.
And the weakest link in any system, from my point of view, is still the human being. I mean, this is also, if you look at the example with the milk in the fridge, the third bullet point talked about, well, you still have human beings in the system. I always tend to say to colleagues, if I look, for example, also at traffic in Bangalore, which is something people always discuss about, to my point of view, if we would really have autonomous vehicles, that would be a solution. But then everything has to be automated. The minute you have only one human being in the traffic, then forget about it. You won't solve the problem.
Okay,
Yeah,
so my question is,
yeah.
I have two questions, basically.
Okay.
The first question is this IoT, which is now set in motion. How does this affect or impact the conventional or classic production, manufacturing, and the impact it has on the value chain, the manufacturing value chain? The second question is, since there's a lot of interdisciplinary collaboration that is now required because mechanical engineering is coming close to IT, I assume there's a high degree of standardization that will be needed. And what is Siemens doing, in this area, since you're also, leading and pioneering this? So these were my two questions.
See, number one, if you look at it in terms of manufacturing, I mean, with the automation of the factories, of course, you will have an increase in productivity, efficiency, this kind of topics. On the other hand, you can also, just to give you one explicit example, you can have a much, much higher guarantee that systems will work. For example, when we built the train system from Barcelona to Madrid, this is a high-speed train, and the way we sold it to the colleagues in Spain was that we guarantee a run rate of 99.9%. And this is only possible with predictive maintenance. That it means what we do is, in principle, we collect data, and we know exactly which part of the train has to be replaced before it fails. This is what is predictive maintenance. If you look at data, for example, I mean, if I look at the installed base of Siemens devices all over the world, be it in wind power, be it train system, be it in medical environment, we produce every day 200 terabyte of data. 200 terabyte of data. And this information is used, analyzed. This is then when it becomes from big data to smart data to control the systems better. And the owner of the high-speed train in Barcelona to Madrid, they, for example, guarantee you an on-time ride. If it's 15 minutes late, they will give you the money back. And this is something also, some contractual obligation that we have at Siemens, that we ensure that the train is always on time. And I can tell you, out of 2,300 rides so far, there was only one case where there was a delay of more than 50 minutes, and in this case, people got the money back. So higher efficiency, higher productivity, reliability of the system due to the big data and the analysis. In terms of standardization, I mean, you've seen this recommendation for the industry, how to implement the Industry 4.0. That is one topic where we contribute as Siemens, because the Industry 4.0 initiative has been driven by companies like Bosch, but also companies like Siemens, so we are one of the main partners for Industry 4.0. And the second topic is our platform, which we announced yesterday, Synalytics, where we really try to provide a standard in industrial communication for Internet of Things or next step Web of Things. This will be available not only for us, but for whosoever would like to use this as the platform for Web of Systems and Internet of Things.
Thank you.
Welcome.
Hello, Gerd. I'm from Accenture, and we have been part of the Industry 4.0 exercise with the German government, so very glad to see this, the topic you have discussed. However, one question comes to my mind, the maturity of German manufacturing sector and Indian manufacturing sector may not be at the same level. In India, there's still a lot of manual component in manufacturing. If I look at the skills of the workers, there's a lot of opportunity to upgrade them. What are the challenges, probably a question both for you and Mr. Kirloskar, what are the challenges you are seeing in adoption of Industry 4.0 in India context, given the maturity of the manufacturing in India today? Is it's just simply a IoT play, or are there some prerequisites before you really get ready for Industry 4.0 adoption?
Well, from my point of view, number one, it's a stepwise approach. You not necessarily have to implement everything what I've mentioned before in detail. I mean, if you look at the 3 topics that we are offering from Siemens, you could also, for example, start with topics like manufacturing execution systems, where you focus on, let's say, maintenance management and things like that, so you don't have, let's say, today you have a plant where everything is done manually, tomorrow everything is automated. The other topic probably is what has been mentioned already before, the topic of skill development. That you really have people who have the higher skills so that they are able to operate such kind of a highly automated plant. And I mean, there are a number of programs underway in India also to focus especially on this applied education, where you have, let's say, a universal education plus the knowledge how to operate a plant. There are programs I know from Bosch. We also have programs which have this dual concept of education to get this into the country. Don't know if you would like to add something, Mr. Kirloskar, because you probably know it also a little bit better because you run a number of plants here in India.
Let me just look at it a little more philosophically. If you look at whether it's industry 1, 2, 3, or 4, what has been the reason these things have come across? Really customer demand and competitiveness. Its ability to, the customer wants more, whether it's when the steam engine came in, people wanted more production, people wanted it cheaper, and that's the reason why you start using power. You look at all the industrial revolutions along the way, when you looked at electronics in the factory, CNC systems, it was to make things more accurate, little flexibility. What's happening now? If I look at the car industry, every customer is an individual. He wants the car in his own color. He wants the seats different. He wants a different information system. He wants his car to his own spec. So it's the ability to really supply to an individual customer requirement. And finally, to really implement, whether it's Industry 4.0, it's really up to it's the vision of the management. Am I prepared to give my customer what I want? If I say, yes, I want to give my customer what he wants, then I start looking at what is it that I need to do that. And there may be some things which are of a higher priority, some things of a lower priority. Automation may not be the first priority. It may be the ability to understand the customer's requirement, split it up into various areas, various matrices, and how do I handle each of them individually? What's the communication right from the customer to my car dealer, to the factory, to the production line, to the supplier? That's a big automation chain and a system we have to look at so that we can make individual cars for individual customers. We manufacture 4 or 5 different models on the same line. Each car, if you look on our production line, even with whatever level of automation we have, is different. Different color, different car, different interior, different spec. It's all done through a certain system. And it's because it's no longer, I'll give a black car to everyone. So it's first is the management's decision and passion that I will do what the customer wants. I will deliver what the customer wants. Once you start with that, then you can start implementing a lot of the other things, whether it's skill, whatever the issues are. But the first thing is very, very important.
in India, then what are the specific problems that we have which are very urgent? One is nice to have, another is it's really must. So what, from all these IoT perspective, I think one is, of course, the traffic. If you can solve that, that'll be really good. So what is that from an automotive perspective that you are looking at solving from an Indian context perspective?
See, if you're talking about vehicles, I think it's no longer a Indian context so much. A vehicle, at one time, you could say, talk on issues like safety. We no longer look at whether there's an Indian safety requirement. We're looking at a global safety requirement. A human being is a human being, whether he's sitting in a car in India or whether he's sitting in a car elsewhere in the world.
But I may not want automation, but there may be...
It's not an issue of automation. How you do safety may not be with automation. It may be with entirely skilled labor. Okay? It depends on each way of doing it. But it's the ability to meet your requirement which is more important. Okay? And Internet of Things is a communication tool. Whether you do it digitally or whether I do it with a pencil and paper is an issue which can be tackled. You can convert the pencil and paper communication to a digital communication. You can automate it through sensors and through a computer. But first, the ability that I will do it is important.
Right, we have time just for one more question, so we can take the last one, please. Yes, sir.
Yeah, thank you. As a entrepreneur, as a new entrepreneur who's just started in the industrial automation sector in India, my question is, what advice would you give from a large-scale manufacturing perspective to, in terms of what are the big top 3 problems that industrial automation startups, aspiring to be part of the Industry 4.0, what are the top 3 problems one could solve for a company like Kirloskar or any other large manufacturing organization in India?
Who's going to take that one?
Is this for me the question or for Mr. Kirloskar?
Would love to hear both your perspectives.
Well, I'm a software engineer, so in terms of production, probably will be a challenge for me to answer this. And especially, we are also working on exactly the same topics as Siemens, because the way we position ourselves, we are the enabler for Industry 4.0. What we try is, I showed you the 3 different value chains, the horizontal integration, the vertical integration, plus the end-to-end engineering. This is what we try to solve with our products, with the Digital Enterprise Suite, plus in addition to provide a platform to enable IoT and Web of Systems. This is the Synalytics. So those are the topics we work at. What I can imagine, in addition, what may be required, if you have a platform, usually platform is always the start. On top of this, and this is also a vision what we have within Siemens, is that there will be a number of apps, some kind of an industrial app store that can run on our Synalytics platform and solve certain problems which are specific to individual companies in automotive industry or in other industries. But which problems those are and which are relevant for which industry, this is something probably where you need to think about and see what kind of applications to develop on top of such kind of platforms to enable IoT and Web of Systems. Thanks.
All right.
This use of technology, let me just talk a little beyond production. I'll give an example. We started a program on 1-hour service in our dealerships a few years back, where you can take an appointment and you come in and your car is serviced in 1 hour and sent back. 60-minute service, express service. It sounds very easy to do. I'll do it in 1 hour, but it is not. It requires it required a complete change in our IT platform. It changed in our logistic platform on supplying spare parts, in our platform on how we service the car. Instead of 1 or 2 people doing it, we had a whole system change in how the car was serviced, and we do the servicing in front of an open window. The customer can watch us do it in 1 hour. So it starts with, if I look at the 60-minute express service, why do we want to do it? It's because we think it's good for cost, for competitiveness, which is cost, delivery, and quality. Quality, cost, delivery, it's most important for that. So I think it starts with competitiveness. The demand for competitiveness, or the requirement for competitiveness, is the 60 minutes service is one of the things we understood. And to do that, we needed to change our whole platform and our way of working. And that's where some of these technologies come in. So it's not only just automation in the factory. It is like how you supply spare parts to the shop in the dealership, how many days spare part. I think we are working with hardly 7 days spare parts in all our dealerships. They order twice a day, and we deliver twice a day. And he's able to do the 60-minute service. So it's a whole lot of changes which happen along the way. So again, I think it starts from a customer demand. How would you stay competitive and meet the customer demand and thus make changes in your own system, or the demand comes for automation and Internet of Things or any other such software and platforms in your own way of working. So you asked for 3 points, so it's really quality, delivery, and cost. Start with those 3.
Thank you.